Hi everyone. So we're talking about beans, continuing with the beans. Now we're focusing the common root beans, the most important species in this genus. As previously said, Natalia, the is important in the American continent. We have to pick area of domestication in the Mesoamerican and the Andean, but the most important feature here in the common beans is in the natural compounds. In special, in the tip we have anti-natural anti-compounds, and also in the cotyledons we have a different compounds like amino acids, very important for the protein, and another element important like iron and zinc. All diversity is stored in the SEAT gene barn in the International Tropical Center. The SEAT belonged a lot of the beans collection, in special for cassava, for beans, and the tropical forage. Today we focus only in beans because it's the most extensive collections in the world, when around 30,000 species of the beans. And here in the table you can see the specific numbers according to each species. Also, SEAT have a very big challenge. They guaranteed the viability and the quality on the seeds in long term, around 12 or 13 years. Now, SEAT have another challenge regarding to the characterize the diversity in the seeds, in special for the promissory accession in the climate chain, and also we have high variability in the nutritional compounds. So study this collection is very complicated because it's very bigger. So the first approach is generate a core collection, focus only in the common beans, and through this analysis and through the specific analysis with hydro plant phenotyping, like the NIRS. So what is this technology? The near-infrared spectroscopy is used by to evaluate what is the interaction between the molecules in the seeds with these reflectants in the molecules there in the different samples. So as you know, the Waverland region have a different elements, and we focus use in the visible range in this part, and also the infrared, especially in the near infrared. This interaction is because in the sample there are different compounds like the carbon and the nitrogen and another organic compounds. This technology have a little advantage. It's a non-destructive method. It's a very speed, or you have a very fast the screening on the seed around one minute, for example. Also, it's ecological friendly. Is the minimum requirement for obtain the equipment, and also when compared to traditional methods for identify the compounds in the seed, this approach is cheaper, but has a bigger problem for development. The different models is requirement have destructive analysis with traditional methods like species or another ones, and also is very sensitive when the sample have a lot of humidity in the seeds. So our analysis, you can see here our equipment. And also we have a very nice tool, the tool table. So it is possible to screen the complete of the seed in this part and generate the different spectral data. In the figure B, you can see all the complete spectrum from the 1300 nanometers from 2,500 nanometers. In this part here is a very summary, the complete core collection. You can see in this part, the high variability regarding to the testa, in the color in the testa. At the moment, we have a very big number for the spectrum. We captured spectrum for domesticate and wild accession. And for each accession, we captured 5 spectrum. And in the moment, we have more than 8,000 spectrum for the collections. The initial analysis is identify what is the variability in these spectrum regarding to the biological aspects. See the sample is domesticated or no, is belong to the wild or domestication session, and also what happened with the color in the seeds. In the first analysis, in the principal component analysis, you can see the diversity, in special in the up part of the graph, related to the seed with white testa. So it's very nice. And the another part, you can see the black testa in the seeds. So with this information, we try to elaborate the different model to estimate the components in the seeds. So we need two elements, the NIRS, plots, the reference values, for calibrate the different models in the BLS analysis. Here, the problem here is very expensive to generate the reference models for all collection. So we select a small sample with 100 wild and 31 domesticated at session, and then account the biological process here and separate the analysis in three approaches. The first, use the complete spectra. The second one, use only the part regarding to the infrared region. And the last analysis is related to what is the most important region to predict, to try to predict the different components. Here you can see a little summary about the methodology and the different sets we use for estimate the models, the domesticated session, the wild session, and when put together, then in the analysis, the domesticated mass wild session. Also, the models use the 70% for the training data set and the 13% for the testing we're helping with the analysis. Okay. As I and the moment I say, we need the reference values. Here is the how obtain the nitrogen content in the seeds. In the photo, you can see the process. We take the complete seed and use a different grinder and generate a floor seed for estimate through a Kendall method the content of the nitrogen. And also in the age graph, you can see the first comparison related to the biological status, domesticate versus wild at session. Here it is important highlighter, the wild has more nitrogen than domesticate. So it is very important to the breeding programs. And also we evaluate what happened, we divide the data in the bigger gene pools and the Andean and Mesoamerican, and we don't have a significant difference between the gene pools. Also, when you have the reference values, the approach in this table, you can see the different approach and the summary of the different metrics when you use the PLS analysis. The most important that you know, we have a very short error, a bigger number of the prediction, and we evaluate 13 metrics for each case. And today I will highlight the results about when put together the domesticate and the wild session in the same model and try to identify what happened here. Only the error were very, very short, around 1.99, and the prediction is 0.4. Also, in the graph, you can see the relation between the prediction and the reference values for the collections. Also, in the analysis, when we want to identify what is the most important wavelengths for this trait and separate the data according to the biological status for the nitrogen, when use only domesticated session, you can see here 10 regions, one important contribution to the models. Also for the wild, only identify 4 regions, and when use the both data set, the wild and the domesticated session, identified 11 regions. Here it is important highlighted 2 regions regarding to the compounds in the seeds. Here in the first vector for the HC compounds, also related to the nitrogen content in this region. As you know, the nitrogen is the main component in the proteins, so it's very nice to identify this part. And in the moment, we're working in additional validation on the model, we select a 17th accession and measure again for the traditional and destructive method, identify what is the difference between the prediction model and the real content in the seeds. Okay, finally, this work is in progress. Today only present the nitrogen content for the seeds, but also we evaluate another compounds in the seed, the minerals and anti-nutritional compounds that is important in the beans. And also I highlighted the best model in the moment is the PLS in interval selection. And also it's very nice this approach because in the CIA germplasm band is not possible or in the whole analysis the destructive for identify the different compounds in the seeds. Also, I want to thank you the different persons that are involved in this project.
Regarding that was a very nice regarding the training data set, you have the wild type and the domesticated ones. But there was, I think it was larger, the domesticated compared to the wild type, right?
Right. Mm-hmm.
So how did you balance it, or if you didn't, did you see an effect on the outcome? Did you think there was an effect on the outcome of your model?
Okay, this divide, the split data into analysis is more try to identify what happened according to the biological state. But the most important for the model is have the all information in all possible values regarding to the nitrogen. So when you put together the data, you have more information in each possible category, so it's more accurate in the model.
Would you fear a bit of overfitting on those bands that in theory shouldn't detect any nitrogen at all, or do you have a better reason why to include them or not exclude them?
Sorry, no gonna do it.
So the infrared gives you your spectrum on different bands, and some bands are going to reflect more certain groups.
Yeah.
Some of them have nitrogen, and those would be the most informative for sure. But I saw that some of the other bands that shouldn't got any information related to nitrogen were included. They were included.
Yeah.
Do you think that could be overfitting, or are you comfortable with that?
I guess, we have two elements here. The normal, you take the seed, a grinder, I create like a floor for estimate what happened with the real seed. Here we evaluate the complete seed. So maybe it's this reason is because belong to the germplasm band, right? Also, as you know, the nitrogen is involved in the different compounds, not only for the protein. So these organic compounds maybe is also evaluated in this approach, but for the bank, it's okay, this approach, because it's not destructive.